when I was looking for images of glaciers and deserts and wind, I also typed in the word ice, and this is the image that came up. So I thought, well, maybe not. We won't stick with that image. We'll go with something more like this. Ice, ice baby. There we go. This is actually my own picture of a glacier on the coast of Alaska. I was there last in a cruise about 2 years ago, maybe 3 years ago. And the blue in this photo is not really enhanced. That is how blue the ice is. That's how blue the area is. And it was a misty, mystical day. You can sort of see the mountains in the background there just poking from the clouds. And we were able to get up close. We had a really good captain of our ship who was able to get in there and not reenact the Titanic with the sinking and everything going on. So we were grateful for that too as a cruise. But I thought this would be a good background image here. And of course, we're just sort of blue all over the place. I have my blue shirt, my blue eyes, and the blue glacier and everything else. I won't change it around when we get to the desert and or wind. I tend to be long-winded anyway, so I'll try not to go too long on our lecture here, but let me go ahead and share our screen so that we can get to our PowerPoint. Glaciers, deserts, and wind, oh my. Of course, the first thing I want to do is share a couple of my own pictures. I do tend to prefer glaciers to deserts. I tend to prefer cooler climates, although desert evenings, even down in New Mexico during this past week, if you're watching this video in September of 2020, it was already snowing in the desert climate there. So it can get pretty cool there, but it's never going to reach 90 or 100 degrees, we hope, global warming, global climate change notwithstanding, up in Iceland. As you can see here, this is the Solheimsjökull Glacier. I mangled that a little bit because I'm not too familiar with this one. I can do Eyjafjallajökull, but I can't do Solheimsjökull Glacier. One of the things that we have in Icelandic are compound words. So they all mean multiple things. But apart from that, this is a picture of a glacier. If you look sort of halfway up the picture and to the right here, you'll see a row of people who are walking off towards the larger part of the glacier in the distance there. That gives you a size perspective of how big this is. But one of the other things to note is all of this stuff used to be filled in. And by used to be filled in, I mean only 10 years ago, this whole thing was just one big ice sheet. It's all melted in that time. Here's another one. And again, for size perspective, look at the people over here on the right. Tiny, tiny people. As we look off at this large Mýrdalsjökull, Iceland. What's happening here is we've had some volcanic eruptions, and the volcanic eruptions have spewed ash onto the glacier. The ash is dark, so even with a lower angle of incidence from the sun, the dark material heats up faster than the ice and snow material, which tends to be highly reflective, has a high albedo, and therefore it's melting faster than it otherwise would. Again, all of this ground level here is the remnant of what used to be under a glacier only a matter of a few years ago. So the glaciers are retreating very quickly. Here's the Mendenhall Glacier, just north of Juneau, Alaska. All of this lake area only a decade ago was covered with ice. There is a visitor center that's maybe a mile and a half from the glacier here at the start. The visitor center used to be right on the edge of the glacier. The glacier has retreated that far inland in just the past half century. So the Mendenhall Glacier is one of the larger glaciers in southern Alaska. It is not too far in terms of geography from this one, which is the Hubbard Glacier, which is coming out onto the sea. And that's why we could see this. And this is the picture I have behind me here. I had a wonderful cruise that was there. Here you can see, again, this is not really an enhanced photo as much as it is just showing you the blue that comes out there. And things were so misty and so blue. I look like I'm black and white here. So it's interesting here. I think that there may have been a black and white filter on my face, but this was a very blue area because of the compaction of the ice. So we're going to look at glaciers, how they play in the hydrologic and rock cycles. I'm not pronouncing things well today, so please forgive me for that, in either Icelandic or in English, apparently. So I know all my Icelandic friends are laughing at me for my mangling of the glacier names there. We're going to also look at the way in which, hello, can this go forward? Thank you. Deserts and wind apply in terms of erosion and changing our environment and our climate. Glaciers are thick masses of ice. Not just snow, but ice. Yeah, so that's vanilla ice, ice baby. And it can form over land and flow over into the sea. But glaciers do form on land, and they move, they shift, and they flow. So we can have valley or alpine glaciers. They form in mountainous areas and then sort of spread down into the valleys, often carving out and widening the valleys. Then we have ice sheets or continental glaciers, Greenland, Antarctica. Then we have ice caps over different structures, as well as sea ice over the North Pole, for example. When we're looking at ice sheets, the largest ones are going to be, you may notice just a little bit down there in Iceland, Greenland and Antarctica are the hugest areas here. And then we have ice shelves. An ice shelf is an area that spreads out over the ocean, over the sea. These are the ones that are more likely to fall off as things heat and add themselves to the ocean. Just like putting an ice cube into a glass of water, that would raise the sea level, the ocean level worldwide. Not by much. I will freely admit that. We're talking a couple of inches here. But when we're talking a couple of inches in one area, we can be talking about more than that in others, depending upon different kinds of geological factors. And high tide, low tide, we've already got areas that are pretty much under sea level already. Lots and lots of people, tens of millions of people worldwide, live in areas that are right at sea level. So raise that just a couple of inches and you've got massive problems. Glacial movements include various kinds of plastic flows. We call the kind of movement of lava magma as pyroclastic, because of course it's on fire. But this is something that sort of moves rather slowly. Things can fracture. What we end up with, especially as things are melting, is we end up with cracks and crevices that will then often tend to grow if we don't have successive times of snow and ice and refreezing. And this will form brittle ice where things will tend to move. One of the things that we see are different zones. We have where things accumulate. Snow falls, rain falls and freezes, and then it tends to move along as more and more presses down from the top and goes further and further down. We get into our zone of wastage. And that is one of the areas where really the terrain is being shaped and changed, especially along the melt area, because we're going to end up with streams that are flowing. as glaciers move, they can move forwards or they can retreat. They can move backwards. Here we can sort of see in just 2 generations, all of this glacier area inside has melted into a new lake. There's a lot less ice and snow on these other sides here. I'm going to try to find a couple of pictures of Greenland as I was flying over Greenland and post those up for you so you can see what used to be completely covered with ice and snow now have lake systems in them, very similar to this. We have glaciers eroding by plucking. They will sort of lift up as they're moving along the rocks. Also, we have abrasion, which happens on the bottom, as you can sort of see this kind of scratching and grooving activity that's happening here. But it doesn't always just scratch and groove. It can also act as sort of like a sandpapery kind of polish. But ice, remember, ice as a natural forming thing is a mineral, and it's a very hard mineral. It can crack other rocks and minerals apart. Different landforms that are forming in glacier areas, include a lot of things that we typically form around mountains. We associate with mountains, like a horn. We have the Matterhorn, a major mountain in the Swiss Alps. And that is called the Matterhorn because it is literally, that's what we call that structure, a horn. Notice we have the circuit here and the arete here. These are derivative of names from that same part of the world. So we're ending up with Francophone or Latinized terms. And other people will pronounce those different ways. So again, don't leave snide comments about my pronunciation on YouTube. Then of course we have the fjords, and that is not a Francophone word for the most part. That is a Nordic word, but that will also happen as we have the formation and the runoff from the different glaciers. Glacial drift will bring different materials down from wherever it starts. And we can see the sort of scratches on this as it's been dragged along. We can see the deposits and the settlement that's here. Till is material that is left there directly by the ice. And then we have stratified drift, which is the stuff that further goes along when the glaciers melt. And I have a cat that is trying to get my attention down below, so don't be surprised if it jumps up here and joins us for our lecture this time. But different kinds of deposits, depositional features include moraines, and moraines can take different kinds of forms where we have the sort of medial and lateral. You can sort of see the medial here going off in the distance here. The lateral ones are up against the side of the cliff. And then we have sort of ground and end formations that we can see. We have quite a number of the sort of the ending points of the last glacial expansions. Notice it goes down in here into south central Indiana. We can still see some moraine activity or some moraine structures from the last glacial advances. Notice a lot here in the Chicago area, lots in central Ohio, over here into Iowa, in the Dakota areas in particular. Where did the glaciers go? Well, you see these blue things up here. These are freshwater lakes. They're not seawater, so they're not like the Mediterranean, and they're not like the oceans. The reason why they're freshwater, those are the melted glaciers. When you freeze water, it expands. So if you froze all of this, it would expand up over the borders. Now that wouldn't go to all of these areas here, but it does explain in part how as things melted, it retreated and it exposed the dry land. So what we have here, of course, is a lot of topography that is reminiscent of the underside of glaciers. So we have all sorts of different ways in which we can look at what's happened there. We have our braided rivers, which we've talked about before. We have lakes, kettle lakes. These are different from crater lakes. These are sort of outcropping. The stuff has been outcropped by the glaciers. We have drumlins, which are small kinds of hill-like structures that are formed as the glaciers are retreating, because it's not always flat underneath, so you're going to get these little structures that are built up that are there. You end up with similar happenings with these kames. Then we have our ground moraines and other kinds of structures that are happening. Glaciers grow in ice ages. They cause a lot of different things to happen, including changing rivers, changing the sea level worldwide. As things lock up into the ice, the ocean levels go down. As the ice melts, the ocean levels go up. One of the effects of the last great ice age was that the ocean levels went down, and Alaska and Siberia were actually connected with what's a dry land bridge over there. So people were able to migrate. Animals were also able to migrate over. And then when the world warmed up and the ocean levels rose again, they were far enough away from each other that it was not any longer an easy contact or an easy migration that was there. So the New World, which is often called the American continents, lost biological contact in many ways with the Old World. So the human beings who had crossed over lost contact with the human beings on the other side. That's one of the reasons why when people came over in the 1400s and 1500s, they brought with them diseases that people in the Old World had long since become immune to, but there was no natural immunity in the Americas. And Native Americans died by the millions as a result of that. So here we can see the glaciers extended, especially in the Middle West and down into Indiana, quite far in terms of where the ice and snow is. All of Canada, sort of maybe just a little bit of a blip over here, wasn't, but pretty much all of Canada. But as a result, also the sea levels went down. We had a huge island of the Bahamas and Cuba down here. Florida was 3 times the size of it was. And we can sort of see there was quite a lot more land that was there. The sea may have been as much as 300 feet or more lower than it is today. The ice age lasted, the last major ice age lasted for a very long time. Began 2 to 3 million years ago. That's a long expanse of time to be thinking about when it started, and ended not too long ago. And in fact, there are many people who think that we're still at the tail end of the last ice age, because we had a little miniature ice age burp just in the last 500 years that ended essentially in the last century. Ice covered 30% of Earth's land masses, and most of that was in the Northern Hemisphere. That's because most of the land mass of the Earth is in fact in the Northern Hemisphere. All of Canada, again, Greenland. You could literally walk from Europe to the United States across this, and there are some people who study animals, archaeological digs about animals, who think that that happened a number of times. Also, human beings could cross over here. And this little land bridge here in the Bering Strait area became one of the areas where people could walk along the seacoast from the areas in Asia, China and Russia, Mongolia, and over into Alaska. And then once they were here, and once the ice retreated from Canada, they spread to the south. But when we're looking at causes of ice ages, there are a lot of, well, maybe this, maybe that. We need theories that talk about why the Earth cools. we need to take into account short-term versus long-term changes. We also have to take into account the fact that our plates move. The Americas have been in different places. Antarctica has been in a different place. Antarctica used to be attached to the South American and African continents, which used to be together. So these things change. The ocean patterns change. Right now we have what's called the oceanic conveyor, and we'll talk more about this later in our course, where the heat transfers all across the globe through various cycles in our ocean patterns. Well, if the oceans are a different shape, that all happens in a different way as well. When all of our continents were effectively conglomerated together in the last supercontinent called Pangaea. Think of Gea as being geology, geography, things about the Earth. Pan as being all, Pan-American Games. Pangaea, pretty much all of the land masses have been connected more than once in our history, but this was the last great connection. Notice the ocean's going to be a vastly different shape, so any circulation patterns are going to be vastly different as well. There are different parts of India and Africa and South America and Australia that used to have major ice sheets that don't anymore, because these areas are now in temperate or hot zones, tropical zones, where that wouldn't fly in terms of it being on the surface. We also have the orbit of the Earth. We're not in a perfect circle. We're in an elliptical orbit, and that shifts a little bit around as the other planets pull on us. So we do wobble in that orbit. We also wobble in our tilt. We're tilted at 23.5 degrees towards Polaris, but that wobbles a bit too over a long period of time, probably about 40,000 years. And then we're also wobbling in what we're pointing to over the course of 26,000 years, and that's called precession. Polaris, the North Star, is not always the North Star, and 13,000 years from now, Vega will be the North Star. 13,000 years from now, midsummer will be the middle of December and January here in Indiana. And it will be, again, the opposite on the southern hemisphere. So all of these things apply to our climate and changes in our climate. So our climate has been changing 100% of the time that we have had a planet. Go figure. So anyone who says they don't believe in climate change, notice when I will sometimes do this in class. If we're doing lectures face-to-face, I will ask who believes in climate change, and some people will put up their hand and other people won't, and I will then say, I did not ask who likes Al Gore. I did not ask who thinks we have man-made global warming. I asked who believes in climate change. Every hand should go up when that question is asked, because in fact, the climate is changing 100% of the time. The atmosphere is changing 100% of the time. Our continents are shifting 100% of the time. Everything is moving 100% of the time. Now, that's not to say we're not making it worse. That's a different question. But notice, and that's something important to notice as well. What is being asked? That's part of science. When I say, do you believe in man-made global warming, that's a different question from, do you believe in global climate change? One of the things I often sort of get a little bit in trouble with are friends who tend to be biblical literalists. Now, I am Father Kurt, as you may know, and I'm a chaplain, and I read the Bible, and we just got through in our Bible study with Noah, the story of Noah. What is the story of Noah? Water. Water covers the entire face of the earth. Guess what? Hey, that's global climate change. Lots of things changed there. The number of people who take the Bible literally but don't want to believe in global climate change is actually pretty high. I often wonder why. That's just a little aside there for you. Your mileage may vary, and I'm happy to talk to you outside of class about what my theological views are. I will save that for another time. But then when we look at other areas in terms of our climate and our environment, deserts feature rather large on our planet. If you look at a globe, you'll see a really big one in the middle of Africa. That's the Sahara Desert. There are other major ones around. There's the Mojave Desert. There are other deserts. Pretty much on each continent, you're going to find a desert or a desert-like area. Europe's about the only exception there, but it depends on how you define desert and how you define Iceland being part of that, because Iceland has some pretty desert-like conditions, although strictly speaking, it might not be a desert. We have air pressure, winds that are often blocked by mountains. So you get a lot of water on one side and not so much on the other. We have deep interiors away from the ocean and sea effects with water in terms of keeping the atmosphere moist, which can also account for that. So here we sort of have in the United States, the Mojave Desert, that's perhaps the most famous of ours, but we have the Great Basin and the Sonoran, and we have several that go down into Mexico and down into South America, including the Atacama Desert and the Patagonian Desert. The Atacama Desert, I know as an astronomer pretty well because there are lots of observatories being built in the mountains there. You can have desert areas that are in very hot areas like the Sahara and the Arabian deserts. You can also have them in temperate areas, which is the great area here in Australia, the Simpson and Great Sandy areas. But you can also have them edging into much cooler areas like the Patagonian Desert here, the Great Basin area going up into Idaho and Oregon there. We also have the Turkestan and Gobi Desert areas, which get into rather cold areas. There's lots of freezing temperatures, not a lot of precipitation in the Gobi Desert in China and Mongolia. So we have dry region weathering that happens there. So chemical weathering, but not a lot of water-based kinds of changes that are taking place there. We have stream beds that only run when the rain is falling. So you're going to have a lot of dried up riverbeds in areas like that. That happens quite a lot, say in Israel and in northern Arabia, Saudi Arabia, and in Jordan. You'll have a lot of areas that will bloom, but they'll only bloom for a couple of days or a couple of weeks because by then the water is gone and it doesn't come again for another 6 months to a year. One of the things that can also happen if you have rainfall that's too heavy is you get flash floods because the land is just not used to that kind of water happening along the way. So we end up with ephemeral streams. Ephemeral means it sort of comes and goes, and you can end up with these huge pouring outs of water, a large volume of water that's going through here at a short amount of time, but for the rest of the time, it's dry. What we'll see with a lot of things like the desert areas and the basin areas is we will have uplifted or up-tilted areas of our continental crust. So the Great Basin, for example, is between the Rocky Mountains and the mountains on the coast of California and Oregon. Then we also have different kinds of structures that will over time wear down. So here's what we are sort of seeing. Once upon a time, we had earlier mountain areas that ended up being worn down over time. One of the things we also notice is wind erosion. There's actually Sahara Desert dust that will land on the United States every now and then. In fact, earlier this year, everyone was saying, oh, 2020, we have so many things. We even have the Sahara Desert blowing wind onto us. Well, that happens actually every year. It was just a little bit thicker this year than normal, but a little bit thicker didn't mean we all wear gas masks because we're being inundated with sand. this is a global phenomenon, but you can actually pick it up on satellite photos like we see here. The movement of dust being driven all the way across the Red Sea into Saudi Arabia. And we end up with loose material because sand is very, very easy to blow around. Being picked up and blown around, you get sand dune structures that form, and that's often called cantaloupe terrain. We also have this dust and sand acting like a sandpapery kind of thing. So it will act almost like a sandpaper polishing. So as we're seeing in the desert, sometimes we don't have a lot of sand on the surface, in part because the deflation of it happens. The sand gets blown away, but the heavier rocks that are part of the sand get left behind, and eventually that's what covers the surface. But what we'll also sometimes see is as sand accumulates in other places, it will often work its way under the rocks. It will work its way down into the silt. We also have these rocks that are grinding against the underbelly here, and that can create more sand depending upon the conditions. So we have different types of wind deposits. We have what are called the lows, and the lows are things that will sort of blanket the deposits along the way. We get our sand dune kinds of things that happen as well due to the way things shift. But it doesn't just affect sand, because what's happening in this stuff is it's hitting across the different rock faces. If you have even something as gentle as sand against the rock, doing that for hundreds of thousands or millions of years, you're going to be creating a lasting impression. One of the reasons why Mount Rushmore isn't going to last forever, because it's being very, very gently, but it's being sandblasted away. Different types of sand dunes can be formed by different kinds of wind patterns. So we have all of these different kinds of wind patterns that are happening here. One of the things that's happening on Zooniverse, which is a website I may introduce you to a little bit later in our course, is we're looking at these kinds of wind patterns on Mars and trying to figure out the wind patterns based on what's left behind on the land and soil. So these are distinct. Sometimes you might think, well, that looks like a wave pattern, that looks like a wave pattern. These might look like hovercraft pattern kinds of things, but they depend upon the wind pattern, and these are not indicative of water. These are indicative of wind that's there. So this has been a shorter lecture for you, and I hope that I will see you on our extra credit board that I put up. I already put it up if you're watching this video, for the underwater town for Lake Monroe. And look for more extra credit along the way, including, as I mentioned, Zooniverse.